recognition system. And finally, with all the advancements that have happened in the last, say, decade or so, so we have actually moved from ML to deep learning, right? So there's several advancements in this area, and we have now several deep learning architectures. Now, with that, how this approach has changed. Okay, so you can think of this as some sort of a shift in the paradigm. So the way we used to design pattern recognition system, how it has changed with the development of deep learning models or architectures. So I'll briefly introduce that as well, and so we'll understand how this has changed. Okay. So yeah, so anytime if you have any question, anything is unclear, you may interrupt me and ask me questions. So I would like to be more interactive than, just a continuous 2 hour sort of a speech. Now, if we talk about pattern recognition, let's first talk about, for a moment, just ignore pattern. We'll understand what exactly is pattern, why is it called pattern recognition. So let's first understand what is recognition, specifically what recognition tasks that we human beings perform. Okay, so if you look at the recognition task that human beings perform, and in fact we perform it with effortlessly. Okay, in fact we do it on an everyday basis. If you I've just listed a few. There are several other tasks that we perform as well. Okay, in addition to the ones that I've listed here. So for example, face recognition. Okay, so face recognition is something that we perform everyday basis, and in fact this is the primary way we recognize fellow human beings. Okay, so for example, when you know someone, okay, you are familiar with him, your friend or your relative or whatever, right, a family member. Now, whenever you see the person, meet the person, you would recognize the person, you actually perform face recognition, right? This is the primary way of recognizing fellow human beings, okay, for us. Now, how do we do it? We'll briefly talk about that as well, right? How we think human beings perform this, although it's not very completely clear how exactly human beings perform these tasks, okay, these recognition tasks. Now, in addition to that, we also perform speech recognition. Okay, speech recognition, speaker recognition. So now, if anyone can tell me what is the difference between speech recognition or speaker recognition? Do you understand the difference between speech recognition and speaker recognition? Yeah, anyone? Any participants would like to? Okay, so I don't think you're keen. So now let me just briefly talk about speech. So I hope this is clear to you. So now if you've worked on one-dimensional signal processing, this is a perfect example of a speech, is a perfect example of a 1D signal, right? So whereas this, of course, if you have to perform face recognition by machines or computers, yes, you will require an image. Okay, image or a three-dimensional, you can of course perform it with the three-dimensional scanners as well, which capture 3D data and then perform, based on some features, some attributes computed from the data, you can actually perform recognition, right? We'll talk about that later. Here we are talking about how human beings perform these tasks. Okay, so basically speech recognition is all about, so in fact, what you're currently performing is speech recognition, right? So you can listen to me. Okay, so what you can listen to me is a audio, the speech. Okay, and you're able to decode, understand what exactly is being spoken. Okay, the content. So in the speech recognition, it's all about. So it can be performed online. So what you're actually currently performing is online speech recognition or real-time speech recognition, or it can be performed offline as well. In offline, what we mean by offline is you have a recorded speech, for example. Okay, someone said something, you recorded it, and then given the recorded speech, the speech signal, you're trying to understand what was spoken. So maybe the person said hello, and you just have the speech signal. When he said hello, you recorded it using sensor, of course, microphone, and then you're trying to understand what was spoken. So right, so this is So in fact, in speech to text translation, okay, speech to text conversion or translation, the core of that speech to text translation is actually the speech recognition. So once you understand what was spoken, we can actually create the text, the corresponding text. Okay. So whereas speaker recognition, we dealing with the problem is different here. Okay. Although the input is similar, input in the sense, you have a speech signal. Okay. Someone said something, you recorded it, or again, as I said, it can be real time as well. Somebody is speaking, for example, imagine a scenario. So you receive a call. Okay. So you may not have saved this number, but maybe your friend is calling you, right? So you're familiar with his voice. Okay. You're familiar with his the characteristics, the voice characteristics, and you may not have saved his number, so therefore, the name does not appear on your phone these days, right? So then, because you're familiar with his voice, you can immediately recognize the speaker. Okay, so here the problem is, this is also a recognition problem, but in this case, you are interested in who the speaker is. Okay, so if you're performing it, for example, offline, you have a recorded speech, someone spoke something, okay, and then you're trying to identify who the speaker is. Okay, so that's speaker recognition, right? Whereas speech recognition is all about the content, what was spoken. Here we are trying to identify who the speaker is or who the speaker was. Okay, and then you have some other recognition tasks that we perform. Okay, human beings perform, again, as I said, on an everyday basis, right? So for example, in fact, you're currently doing that, right? So I have written here voice. Okay, so you can read. So here this requires some sort of language familiarity, similar to speech recognition, for example. Okay, so if you're familiar with the language, you can understand the speech, you can recognize the speech, the content. Similarly, what was written, it can be handwritten, typewritten as well. A lot of text here is typewritten. In addition to that, whatever I write, it's handwritten characters. So you can read, recognize, understand the context. Okay, so the entire inference. Okay, so you can actually make sense of it, right? So that's what you're trying to do here. So these are some of the recognition tasks that we perform, human beings perform on an everyday basis with not a lot of effort. Of course, as in the childhood, our brain also, as our brain develops, we learn a lot of things, and in the process, the brain is trained to perform all these tasks. Okay, but we don't do it explicitly. Okay, but when it comes to what is now pattern recognition, pattern recognition is the field or the domain where we are interested in designing machines in general, or you can say program computers. Okay, so we're trying to provide this ability, whatever we are able to perform with effortlessly, without much effort. So we are trying to provide, or we are trying to enable computers to perform that. Okay, so we're trying to design machines or computers, machines in general, because as I said, this could be, for example, not necessarily computer, it can be a robot, okay, performing. In fact, the current day robots will have all these abilities. It can perform face recognition, speech recognition, speaker recognition, several of these, right? So just like our human beings, all the abilities we expect it in, of course, in a general purpose robot, for example. Now, that's what we call pattern recognition. The reason why we call it pattern recognition is, so now if I ask you how you think we human beings perform face recognition, so what would be your answer? How do you think human beings perform face recognition? What do you think we rely on? Okay, what are the features we think rely on? So again, there is no very clear cut answer, because if you look at how we perform it, look at it this way. We have sensory organs. For example, primary sensory organ for this is our eyes. Okay, so we can look at a certain thing, we can look at a scene, we can see the objects in the scene, and immediately it's actually a so seamless process. It's not like a camera. Our eyes are not like camera, right? Camera can only capture an image of a scene, whereas our eyes can see the scene and immediately sort of pass on that information to the brain. Okay, so once it's passed on to the brain also processes this information sort of, again, seamlessly. We don't see that, the latency and so on, right? So, and then we can immediately make a sense of it. Okay. So when you see something, we do not explicitly process it, right? We see that, immediately make sense of it. Okay, that's how, and in fact, that's what we call, the entire human vision system. Okay, so it's a complete human vision system. So it's not working independently, right? The eyes are not working independently. Uh, with the help of eyes, we see the scene, and then immediately the brain processes that information, and then we immediately some derive some useful information, right? Make some sense of it. So that's the complete human vision system working, in a seamless way. So what we're trying to do, in fact, in computer vision, we try to do that, right? So we try to provide that ability to machines. Okay, just like how human vision works, computer vision, in computer vision field, the objective is to actually design machines or computers, program computers that can perform just like the way human vision system works. Okay, now, so in fact, you can see here, that's also an important point here that I want to emphasize. So pattern recognition is not just something that, it's sort of, independently. There's a significant overlap between pattern recognition field and computer vision. And then, of course, biometrics also is it's sort of an applied area. So for example, this problem where we are interested in identifying who the speaker is based on this input, which is the speech input, one-dimensional signal. So it's actually a biometrics problem. Okay, so this is actually a biometrics problem, whereas here you can consider this to be a pattern recognition problem along with it, because the input is an image. Okay, it's a computer vision problem. Okay, so it's a computer vision problem we are actually going to solve using PR concepts. Okay, so that's why I'm emphasizing on the pattern recognition concepts, because this is applicable in multiple fields. Okay, so I have not mentioned some biomedical applications as well. Yes, there are some biomedical applications as well. For example, let's say you have an ECG or an EEG signal. Okay, let's talk about EEG, for example, or ECG for that matter, right? So you have this clearly, this PQRS patterns. Now, what sort of recognition that you can perform? Of course, human beings, we may not be able to perform, but a trained person, a doctor, can look at the ECG. Okay, so for example, there's a patient, there's a person who develops chest pain, goes to the doctor, and then doctor advises ECG, and then a doctor can actually look at because he's trained, can look at the ECG and decide whether this is normal or if there is any issue with the heart, the condition. Okay, so abnormal, for example. Let's talk about simple, So basically, this is a recognition problem, right? So although you can think of this as a specific classification problem, given this input, ECG input, we are performing classification, whereas recognition is more a broader term. Okay, so I'll introduce that as well later. So recognition is a more broader term which actually encompasses this classification as well. So classification comes under recognition. Okay? In fact, several of these recognition tasks that I've written here, as I've listed here, these are classification problems. Okay, and but recognition involves beyond that. We'll talk about that as well. Recognition is, again, I'm repeating, it's a broader term, whereas classification is a very specific, much simpler task. Okay, so you can think of this as a recognition task as well. Given an ECG signal, you're processing it. In fact, here the human being, the trained doctor, is performing it, and then he's trying to diagnose the issue, as normal or abnormal. Now, again, so what does it depend on? If you ask the doctor, yes, he will say that he is familiar with the pattern. For example, he knows what exactly is a normal pattern, how should it be in a normal circumstances, and what can be the abnormal patterns, what abnormal patterns that are typically, that manifest in the ECG. Okay, or for that matter, EEG, and you can think of epileptic seizure, non-seizure, and so on. Okay, now, so again, all those, as I said, depending on your area of research or area of interest, everywhere you'll find this recognition task. Okay. Now, why do we call them pattern recognition? The question comes back to, so for example, if you ask the doctor how he performs this classification, how he performs this recognition task, so he might say, yes, he knows, how should a normal pattern be, and what are the possible abnormal patterns are the deviations from the normal pattern. Now, so that is what we call pattern. Okay, So based on the underlying patterns in the data. Okay. So data actually, for a layman, this may not make much sense, but for a trained doctor, he can actually look at it very closely and see some patterns. Now, if the patterns are normal, he would diagnose it to be normal. If there are some deviations, abnormal patterns, he would say that it's abnormal. So basically, the recognition is actually performed based on these patterns. Okay, so the underlying patterns, the data, underlying patterns in the data is what this is based on this, we perform this recognition. A similar case, if you talk about face recognition, yes, all of us can perform face recognition. Now, if I ask you how you think we perform face recognition, okay, very similar answer. You might say, yes, we might depend on patterns. Now, specifically, what are the patterns? Here, the facial features. Okay, for example, the shape of the eyes, maybe the width of the eyes, length of the nose, the shape of the jaw, and so on, right? Multiple things. So in fact, I'll talk about how exactly the first completely automated face recognition system, how it was developed. Okay, so what were the sort of thought process, the person who developed this first completely automated face recognition system. So what were the features that he employed? Okay, he relied on, that the method relied on rather. Now, so that's why it's called pattern recognition. So as I said, sometimes since this field also is referred to as pattern classification, because recognition is a more broader term, classification is a specific problem. Okay, so we'll talk about, as I said, broader term. So you might be interested in knowing what are the other things that come under recognition other than classification. We'll talk about that also briefly. So again, so if you're designing machines, yes, you need to acquire some data first. You can think of this way, right? Here I've listed them, all these tasks, all these recognition tasks that we perform. Now, if you have to develop a system, if you have to develop a machine that performs these tasks, okay, then you need to acquire some. We also acquire, in fact, so you can see here speech. Okay, we have our sensory organs, ears. Okay, here we have eyes, ears. Okay, and then again eyes. So sometimes we perform some odor recognition also, right? We can smell, we can perceive the odor and then try to recognize. Although we are not interested in such things, we can of course have some sensors, appropriate sensors that will that will sense this and then sort of generate corresponding electrical signals. Using processing that, we can again perform that, but we are not going to talk about that. So more or less we are restricting in our case in pattern recognition to mostly image based or one dimensional. So these are image based recognition tasks, whereas these are one dimensional signal based recognition tasks. And similarly, as I mentioned, give you some examples from the biomedical signal processing area. So you have ECG, EEG, all are one dimensional signal processing based pattern recognition tasks. Now, every time we need to acquire, if we are trying to build machines or design machines, you need to acquire some raw data. So you require some sensors. So I'll present that pipeline as well, the complete processing stages. So you require an appropriate sensor. Okay, so it depends on, for example, if you're performing face recognition, it would be a camera. Okay, so speech will require microphone. Speaker, again, speech. So input is a speech, so you require microphone. And for this, again, camera. So for example, you can even perform three-dimensional. So if you want to use some depth features as well, okay, three-dimension, because face is a three-dimensional object having some depth information as well. So if you want to utilize that as well, so you require a 3D scanner. Okay, we will not go into the technology of the acquisition. Okay, so similarly, as I said, ECG, EEG, you have electrode based, ECG data capturing and so on. So you have sensors for that, right? So you capture the raw data, process them, and then finally decide the category of the pattern based on the patterns in the data. Okay, and we decide the category, and that's exactly what pattern recognition is all about. Now let's look at the processing stages, okay, or the pipeline, how exactly we do it. So you can see here, so if when you're performing this, machines are performing pattern recognition. When you develop machines to perform pattern recognition, essentially it involves analysis of the acquired data. I'm mentioning data repeatedly because data can be specifically, if you talk about it, it can be, it can be one-dimensional signal, it can be 2D signal, which is an image, okay, input, or it could be 3D data as well, okay, so 3D data and so on, okay, so it depends on, so it can be other forms of data as well, but it typically broadly falls under 1D signal or a 2D signal or an image, okay. So now, yeah, the first stage is sensing. As I said, depending on the problem, you need to have an appropriate sensor. Okay, so I think that that's familiar to you now. So how you select sensors, and so we're not going to discuss this in detail. This part of it. This is of course some sort of a hardware that will sense from the real world and then give you some data. Okay, so this is what we call raw data. At this point, it's the captured data, the acquired data, which is what we call raw data. And often the next stage of processing is, we actually refer to this as pre-processing. The reason why we call this pre-processing is the core, okay? The most important stage of this pipeline is this stage. Of course, this is also important, but I feel this is the most important stage. There's a reason for it. We'll talk about that as well. Now, the reason why this is, and the reason, because this is the most important stage, anything that precedes this, we call it pre-processing. Okay, so this is the most important processing stage. So anything that precedes it, we call it simply pre-processing. Now, what is the role? What do we normally perform in pre-processing stage? As I said, at this point, you have some raw data, raw signal. For example, if you're performing speech recognition, you may have just the acquired speech. Microphone is a sensor, so it acquires some speech. Now, the speech may have some noise. Okay, so speech may have some background noise and so on, right? Multiple things. So you may want to reduce. So in the pre-processing stage, you perform all such operations, all such processing. So for example, denoising, or simply noise suppression, okay. Or if you're talking about some image that you capture, you may want to enhance the image, improve the image, okay. So we may perform enhancement. For example, some of the simple enhancement techniques are histogram equalization, contrast stitching, and so on. Okay, so all this can be part of your pre-processing stage. In fact, if you're talking about face recognition, so you can think of this way. So the person, okay, appears here. Now you have a camera, sensor is a camera that captures image. It's possible that you capture an image, you have a person, but at the same time in the scene, you have several other objects. Okay, so you may have a dog here, you may have a car parked here, whatever, right? You may have a cat and so on. So multiple objects in the image, in addition to the image of the person who you are trying to recognize. Now you may want to just, because we are going to perform face recognition, you may want to just focus on this part of the image for further stages. So therefore, the first stage, in the pre-processing stage, you may perform what is called face detection. Okay, so face detection can be part of your pre-processing stage. So given this image of a scene having multiple objects, so we may just want to localize the object of interest. Okay, so the object of interest in this case is the region of interest. Basically, region of interest is, in this case, is a face, human face. So detecting that given an image is actually called face detection. That can be part of pre-processing. Once you have that, so remember, at the output of your pre-processing stage, it's always the same data in the sense, the data in the same format. So if this is a 1D signal, this is also a 1D signal. For example, you have a speech signal, noisy speech signal, this is a denoised speech signal. So if you have an image, this is also an image. Okay, but of course the data is not the same, but it's processed. Okay, so it's processed for noise suppression, noise removal, or enhancement, and so on. Multiple, you can have, depending on the application you may have other processing also that you perform on the raw data that you capture. So this is a much better, improved version of your data that you acquired here. Okay, so otherwise the format remains the same. Okay, now so this also is a data. It can be a one-dimensional signal, image, and so on. Now at this stage, this, as I said, is a most important stage, and this is called pattern representation. What exactly, or more popular term, is actually feature extraction. Okay, so you may have heard of this, but these days this has become more popular. There is a reason why I'm referring to this as more popular term. We'll talk about that as well later. Now here we're saying it's pattern representation. Why is it called pattern representation? So as I said, so when we perform these recognition tasks, we depend on the underlying pattern. Okay, so we expect this machine or computer also to depend on the patterns in the data. Okay, underlying patterns in the data, and then try to perform recognition, or specifically if you're talking about classification problem. Okay, now so for that to happen, we need to capture the patterns in the data. Okay, something in a very concise form. Okay, so you have this data, image, signal, and so on. So this may have a lot of unnecessary details as well. From this data we need to obtain what we call a representation. Okay, so this is what we call representation, or in in simple terms, a feature vector. Now this process of obtaining this representation, which represents the important patterns in the data, and that is why this stage is called pattern representation. Okay, this represents all the useful patterns in the data. Okay, and simply we call it feature vector because we can think of these as individual elements here in the representation as features. Okay, we'll talk about that specific examples later. So you have a set of features forming a feature vector, or we call it simply a representation that represents the underlying patterns in the data. So once we have captured this, how do we do it? We'll talk about this also, because this is one of the most important stages here. How this is traditionally is done, how, with the advancements in machine learning, how things have changed, okay, in this stage now. Once we have this, so basically this is a numerical feature vector, basically numerical vector. It can be a 1D vector, one-dimensional vector, or it can be a 2D vector. 2D basically is a matrix, okay? So you can have a two-dimensional matrix depending on the problem, depending on the techniques that we use for feature extraction, okay? So, or pattern representation. What are the typical conventional techniques? We'll also talk about that. Depends, of course, on whether it's a one-dimensional signal or a two-dimensional image and so on. Okay, so but that's all that it does is, given this data, it actually obtains, computes a very concise representation, okay, of the data, and based on this, you have the final stage that makes the decision. Now this decides, for example, you can think of, this is, for example, a ECG, right? You have a patient here, so you have a ECG capturing machine, so which captures the ECG. So you may perform this may not be always part of it. If it's not required, you can just remove this as well. So, okay, if the acquired data is it's absolutely good, no noise, no pre-processing required, you can just pass it on, right? You can directly perform feature extraction, and then based on the features, you would try to decide whether this is, the machine will try to decide or predict whether the ECG is normal or abnormal. Okay, so even for example, face recognition problem can be treated as a multi-class classification problem, right? So if you're trying to develop a face recognition system to recognize, let's say, 100 people, okay, you can think of this as a 100-class problem. So of course a multi-class problem, but you can, if you have 100 people enrolled for this system, or authorized people are trying to recognize 100 people, you can have a 100-class classification. You can consider this to be face recognition to be a 100-class classification problem. So this is where, in a conventional pipeline, machine learning comes into picture. Okay, so until this, of course, this is some sort of a hardware to sensor which acquires data, and these two stages where this is where you have all signal processing, image processing, techniques utilized. Okay, so all signal processing, image processing techniques are utilized in this stage. Okay, so you require a lot of signal and image processing expertise to develop algorithms for pre-processing, algorithms to extract features, and so on. Okay, but finally, based on these features, okay, so this is where machine learning comes into picture, specifically a classifier. Okay, so I believe you're familiar with classifier, which basically it's a supervised learning technique, right? You give a pattern, for example, and you tell, during the training stage, you tell this model that yes, this belongs to. So for example, you have an image of a person. Okay, you compute certain features, facial features from this image of that person, and tell that model that yes, this is the features of this person, person X. Similarly, you acquire another image of another person, compute the features, and then tell the model, yes, this is of person Y, okay, X, Y, and so on. So every time you provide an input, corresponding output as well. Okay, so this is a training stage. This is how you train a model, a machine learning model in a supervised setting. Okay, so once you train, yes, when you provide an input image of this person, say a different image of the same person, you expect that that features are similar to this features that we earlier computed, and we'll talk about that as well. What are the desirable properties of these features and so on. So you expect the model to predict that yes, the person is X. Okay, that's what we call face recognition, or in any other classification problem also will fit into that same. Um, Now, as I said, in a traditional pipeline, this is where machine learning comes into picture, specifically a classifier that requires training. Okay, so you need to collect data belonging to multiple classes, multiple examples belonging to different classes that you have. Okay, so if it's a two-class problem, we typically call, in machine learning, we call it binary classification problem, right? So for example, if you're trying to classify an ECG signal as abnormal or normal, so it's a binary classification problem. Okay, so then it's of course a simple problem. Binary classification compared to multi-class classification is considered simple. Okay, simpler. Now you need to train the model, and then once the model is trained, you can plug it in here and then provide any input. So provide this input here to the machine learning model, and it will predict the corresponding class, okay, the class label. So this is how the conventional pipeline works. As I said, the focus has always been, although yes, machine learning researchers, mostly from the from the domain of computer science, they focused on developing different classifiers. For example, the earlier simple classifiers were, for example, you can think of multi-layer perceptron. Okay, so started with neuron. We'll briefly also talk about that. Okay, and uh, and then because that still forms the sort of foundation for the recent developments in machine learning, right? So we have moved into the deep learning, domain, but the foundations still are, the basic, the simple model, mathematical model of our biological neuron, the operation that performs. Okay, that still remains the building block of your deep learning models as well. For example, convolution and neural networks and so on. Now, so therefore, we'll briefly talk about this. But then there has been several advancements. For example, this model, you have decision trees, you have random forest, and you have support vector machine. So several classifiers have been, and a lot of variants as well, and these are some of the classic ones, and several of these variants have been developed. At the same time, parallelly, we have had several advancements in this area also, right? Specifically, if you talk about one-dimensional signal processing, so you have researchers have focused on denoising techniques, enhancement techniques, and so on. At the same time, feature extraction, mostly these were based on some sort of frequency domain representations. Simple techniques would be, for example, short time Fourier transform, and then you have time frequency representation techniques like wavelet transform, discrete wavelet transform, and so on. So a lot of these techniques were used to most of the time in the one-day signal processing domain. This is transformations, right? Transforms were used as feature extraction techniques. So once it's transformed, you have a very compact representation, right? We know the certain properties of the transforms as well. So you get a very compact representation of the original data, and which can be used as features, right? In addition to, of course, you can compute some more explicit features as well, and that's what typically we do in image processing. So if you have an image, as I said, if you have a face image, and if you're performing face recognition, you can always extract some explicit features like width of the eye. That can be one feature, one independent variable. Width of the right eye can be the other independent variable. Length of the nose and so on, right? Multiple shape of the jaw, you can capture some angle measurements here. So you can put together all these features to form a feature vector. Or you can, of course, there are some generic feature descriptors as well. We'll talk about, for example, local binary pattern and so on, so which are more generic. So, they depend on texture in the input. Tries to capture the texture information in the input, in the image, and encodes it into a feature vector. Okay, so these are more generic feature vector. We'll talk about those as well briefly. And so the point that I'm trying to emphasize is there has been a lot of research in this area trying to develop, even in one dimensional signal processing, the classical transforms, and in addition to that, several variants of it, improved variants of these transforms for feature extraction. These were developed, and of course, they achieve state-of-the-art performance at one point. And similarly, in image processing, initially these were mostly domain-specific features that were explicitly captured from the image, but then later on we moved to more generic features. So I'll also talk about that evolution that has happened. And as I said, parallelly, there has been a lot of advancements in machine learning as well. So this is how, for a long time, the research in this area progressed. Okay, so you have researchers working on these techniques as well as these techniques. So these were mainly people who had expertise in signal processing, image processing, whereas this was mostly, researchers in machine learning, focusing on machine learning. Now, yeah, so briefly about pattern recognition, we discussed this in detail already, which is a core of your pattern recognition system pipeline, the stage. Okay, so it involves feature extraction or representation, representing the most important underlying patterns in the data in the form of a feature vector. And sometimes this is not always a part of the stage, but if required, we can also include what is called feature selection. Now, what do you mean by feature selection is, again, there are different techniques for feature selection. Sometimes we also use some machine learning techniques for feature selection, but in general, the problem of feature selection is, given an original set of features. Okay, so let's say you have a feature vector which is of n dimension. So you have an n dimensional feature vector. Now it's possible that some of these features are, in most of the time, as I mentioned earlier, in the conventional approach, we compute this, we identify these features based on some intuition. We think that yes, this might work, this might work, so we include all these features, right? For example, you talk about the face recognition, how in the initial stages, how the systems were developed. So, the thought process has always been, yes, so, let's compute the width of this eye, length of the nose, and so on, mouth, and a lot of these features. Now it's possible that specifically look at this, which is something that I'm aware of. So for example, look at this width of the left eye and the width of the right eye. If you treat them as two different independent variables or features, it's very likely that, in fact, this has been observed as well, they are highly correlated. There's a reason, because human face is symmetric. So, typically the width of this eye and width of this eye would be more or less the same, okay, highly correlated. So if you treat them as two separate features, does not make much sense. If you have two features which are highly correlated, in fact, we call this, in machine learning, we call it multicollinearity. Okay, so if you have a feature vector which has two or more features which are highly correlated, we call that situation a multicollinear, and we actually need to remove some of the features so that we remove this redundancy, because it's completely redundant having two features which are highly correlated. So it's redundant, right? So it's in fact not just redundant, sometimes adversely affect your decision making. So it's important that we identify these features and remove them. And that's exactly what feature selection is about. Some manner identify the important features and retain them. Okay, so basically, given an original feature vector of n dimensional feature vector, reducing it to k dimensional feature vector, where k is significantly less than n. So this is a problem of feature selection. How it can be performed, there are different ways. Okay, typically, yes, in feature selection, this is always going to be a subset of the original feature set. Okay, so you can perform, for example, ranking based on some criteria. You can rank all the features, n features here, and then consider only top k features. Okay, this is just one way. If you can rank these features based on some criteria, based on the importance, descending order. Okay, once you order all the features, n features, you can consider only the first k features and discard the rest n minus k features, and then you can obtain a reduced dimensional representation. So this is a reduced dimensional representation, original high dimensional representation. Now with this, you can actually go ahead and perform decision making with the help of a classifier. Now here comes another category of, you may have heard of dimensionality reduction. They also achieve the same, the purpose is same, although it's done in a different manner. Okay, so but if you use dimensional reduction techniques, for example, the most popular technique, for example, linear techniques are like, for example, PCA. Okay, so principal component analysis is a very popular dimensional reduction technique, dimensional reduction technique. And for example, more suited for classification is LDA, which is actually sort of tailor-made for classification, right? To ensure that the clusters of the data points belonging to different classes, I'll show that as well, the feature space later. So they are well separated. So in fact, this optimization problem in LDA is formulated in such a manner that you end up with, but the objective is the same, okay, same as feature selection. So you begin with an original n-dimensional feature vector. So we want to obtain a lower dimensional representation, which is a k-dimensional representation where k is significantly less than n. However, this here we do not just retain the important features, we actually perform some transformation here. So I mentioned here linear, which means a linear operation. Basically, it's just a projection. Okay, so we identify the directions. If you look at it from the linear algebra perspective, most important directions for projection, and then project this high dimensional data point onto those directions. So we obtain a low dimension. Basically, you can think of this way: this undergoes certain operation. Okay, so it basically dot product operation in projection is nothing but dot product operation. So to obtain this lower dimension representation in the PCA, the objective is to actually not lose much information in this process of reducing from n dimension to k dimension. You do not want to lose much information. That's exactly what PCA tries to do, whereas LDA is a different objective. There we want to perform very similar. Yes, the goal is same. We want to reduce it from ND to KD, but then we want to have as much separation as possible in the reduced dimension, okay, in the reduced feature space. So of course, you can also employ this, and people have, of course, employed this dimensional reduction techniques also. So given an original feature vector, they perform dimensional reduction, obtained much lower dimension representation, and then perform the final decision making with this set of features. In here, we may not be able to call them directly as features because they will not directly relate to this. Okay, that's one, of course, one drawback of this dimensional reduction techniques as compared to feature selection. You lose that you know sort of interpretability. These are not features anymore. These were original set of features. These are not features because they have been transformed now, right? So they undergo certain operation. So you cannot directly relate this to, for example, here this could be, width of the eye, width of the right eye, left eye, and so on. But you cannot say that, when you talk about these set of features, the reduced representation. Finally, yes, so that's about pattern representation stage. And then you have typically a classifier which requires training. So that's why I said, learned classifier, basically a trained one. A trained classifier, you need to train them, and then it can perform classification. Now, talking about, so as I said, for decades, researchers, mainly in signal and image processing, they focused here. Okay, this part of these stages of your PR system. Okay, so trying to develop better and better, superior feature extraction techniques, pattern representation techniques, superior pre-processing techniques. Okay, and so most focus has been on this. Actually, much more than this, the focus has been on this. Okay, here we use, most of the time, we use some standard existing techniques, not in all cases, but in most cases, right? For example, denoising, enhancement, you have some existing, well existing techniques, but focus has been more on this, trying to develop superior feature extraction techniques and feature dimensionality reduction techniques and so on. Okay, and at that point, it's important that you identify the desirable properties of features. Okay, so when I say features, I'm referring to these, whatever you obtain, these are features. Okay, so what are the desirable features? So with that in mind, if you're aware of the desirable features, you can try to develop techniques that will compute features that have these features. Okay, that properties rather, features or properties rather. Okay, so now, so of course there are multiple properties that are desirable in features. Now specifically, let's talk about these two most important features, most important properties, okay, of these features. And what is it? One is discriminability. Now what do you mean by discriminability? Is, yeah, again, if you have any questions, yeah, please feel free to interrupt and ask me questions. So otherwise, we'll just continue. Okay. So now, when you talk about discriminability, I'll give you an example. Let's try to understand it that way with the help of an example. So now let's talk about face recognition, which we've been considering right from the beginning. So you have an image of a person. Okay. Now, so you've decided already, some set of features that you compute from this. So you've developed some image processing algorithm. Of course, when you have a program, it can automate it in an automated manner. Given this image, it can compute these features. Okay. Now, this is computed. This set of features are computed from this image. The same person, we capture another image. So this, maybe let's consider that this image has been captured in a, during the daytime. So it's a well lit condition, well illuminated condition, and then so it's all the features are nicely visible. Good set of features. Now, whereas this in a night situation, whereas a low light condition, okay, but of the same person remains the same. Okay, so you again compute the same set of features. Now tell me, when you compare these two features, okay, so when you have a feature vector, you have a feature vector, how do you compare? Okay, so let's, of course the classifier does this part, but here let's talk about some sort of comparison. So if I give you two feature vectors, how do you compare? What are the techniques that are available? What is the simplest way you can compare two feature vectors? So are you familiar with this, or? Yeah, if you cannot, okay, it's good. So yeah, if I'm not sure if you can unmute yourself, or you can just type in your, your comments or questions in the chat box as well. So let me see, there's a question here which was asked. Is it possible to classify or recognize faces using point cloud image instead of normal? For example, yes, in fact, that's what I said. Uh, yes, it's very good. Krishna, that's correct. Yes, that's correct. In fact, yes, cosine similarity can also be used, but yes, Euclidean distance is the most simplest way, right? In any context, given two feature vectors, okay, numerical feature vectors. So if somebody asks you to compare, right, to see how similar they are or how dissimilar they are, the first thing that you go for is Euclidean distance. Of course, you can have cosine similarity or some other distance or metrics, but this is the most popular one. I'll come back to that, but there's a question here about point cloud. Yes, as I said already, okay. So here I did mention that, when you talk about, yes, 3D, for example. In fact, the 3D scanners also, most of the 3D scanners, they actually do not capture the data on a uniform grid. Okay, so if you capture the data on a uniform grid, yes, it becomes a regular 3D. But then typically this is non-uniform. That is what we call point cloud. When we have, what I mean by point cloud is you have set of x values, set of y values, and set of the depth values. Okay, so this is what we call, so specific x value, specific y value for that point. What is the depth? So this is with respect to some coordinate. So you have some coordinate. Let's, sometimes it's camera dependent, camera independent. Okay, so based from that particular coordinate, distance from, so you have the object, so x, y, and z. So distance of this point, okay, so x, y, of course, on this plane, and then distance from this reference one to the object. So that is how you compute the point cloud data. So yes, with that point cloud also we do perform, so we have more information with that. It's not just these cameras, 3D scanners, they will also capture a registered 2D image. So in addition to the 2D image, we can also get the depth information. And if you rely on depth information, you can improve the face recognition accuracy. So it's possible. Yes, as you mentioned about some other scanner, radar, micro, millimeter wave radar. Yes, they can also be used. People have used millimeter radars these days are gaining a lot of popularity for multiple applications. No, I'm not sure if that has been used specifically for face recognition, but yes, for detecting objects, uh, detecting obstacles and so on. Yes, that has been used. Data captured from the radar. Okay. Yeah. So I hope that answers your question. Now let's get back to this. Yeah, this problem. Yes. Now let's get back to this problem of comparing. Okay. So if you're computing Euclidean distance, yeah, now tell me, do you expect ideally what is desirable? You expect Euclidean distance to be as low as possible. In fact, you want it to be ideally zero. Because remember, although these are, yeah, remember why you want this to be zero? You want this to be as similar as possible. Okay, because why is it so? Because these two images are of the same person. I mentioned that earlier. Okay, so these two are from the same person, and in our context, when I say same person, same class, right? If you want to talk about this in the machine learning perspective, right? The same class, same person means same class, right? Because each person we would treat it as each a class. Okay, therefore, because this is from the same class, these are two data examples from the same class. You want these features to be as similar as possible. So when you compute Euclidean distance, you want this to be zero indicating that identical. Okay, of course, in practice you may not get zero, but what I'm trying to say is ideally, if these two images are of the same person, regardless of the conditions, the changes here, the factors that has changed and so on, we'll talk about that as well. Okay, we want these features to be as similar as possible, identical ideally, and that should get reflected in the Euclidean distance, or whatever. If you're computing similarity, they should be as similar as possible. Okay, so and that exactly is, okay, sorry, I think I missed that point. I'm actually talking about this point here, invariance. So what exactly are we talking about? So what I'm trying to say is, you want this features to be the features that you computed to be invariant to, and that is why the invariance property. You want these features to be invariant to the factors that affected your image acquisition, data acquisition. In this case, the factor that affected image acquisition was illumination. I mentioned that this was in a well lit condition, whereas this was in a very low light condition, night, captured in the night and so on. So the factor has affected your image. However, because they belong to the same class, you want these ideally, if imagine how nice it would be if these features are completely invariant to the factor that has changed, the lighting factor, illumination factor. You would end up getting exactly the same features and your Euclidean distance will be zero. Therefore, you want the features to be invariant to the factors that affect your image acquisition, data acquisition in general. And that is why we call it invariance property. You want them to be, the features to be invariant. Okay, of course this is ideal scenario, desirable. So but if you keep this in mind when you develop this technique, okay, a pattern representation technique, when you develop this technique, if you keep in mind this, yes, you will end up with a better technique. Okay, similarly, in fact, if you look at the face recognition literature, you will see that there are a lot of research on, for example, illumination invariant face recognition. Okay, pose invariant, pose in the sense, person is looking at the same person. Here he may be looking, directly looking at the camera, so we call it frontal pose. So he may be also looking, sideways. You may be looking at somewhere. If the object is not cooperating, typically it happens, right? So in a surveillance scenario, so you cannot expect the object to be the person. When I say object, the person to be looking at the camera all the time. Okay, so but yes, if it's a control situation, yes, you can ask the person to, if it's in a very cooperative environment, you can ask the person to look at the camera, capture a nice frontal shot. But that may not be possible all the time. So you may be looking at some other, and pose angle may be different. So that can also cause a challenge. In fact, mask. Okay, so user may be here, he may not be wearing any mask. Here he may be wearing a mask. Okay, which means part of the region of interest is not visible. You cannot extract any reliable features from it. So all these are issues. So despite those issues, if your final features that you compute, if these are invariant, that's what I said, in the literature, there are techniques that are illumination invariant face recognition, post invariant face recognition, partial face recognition technique, and so on. Okay, so there are a lot of things, not just in face, but other domains as well. So all the, I think that part is clear to you. So intra class, why intra class? As I said, intra, within the class. So because we are looking at the same class, okay, so same person, image of the same person, but captured in two different conditions. That's why we call it intra class. This property is actually related to intra class. In fact, similarly, we talk about interclass. So let's look at that. So you have an image of a person. Okay, this is class 1 or a person 1. So you have his image. You compute set of features from this. You have image of another person. So class 2, two different classes. Okay, that is why interclass. Now again, you compute the same set of features, whatever you have identified. Now, what do you expect? If you want, when you want to compare this, when you compare these two features, let's say you use Euclidean distance to compare it. So what sort of Euclidean, you want this to be as high as possible, okay? Because you want these features to be as dissimilar as possible. When I say dissimilar, Euclidean distance will be very high. Okay, so that should be reflected as a very high Euclidean distance, indicating that the features that are being compared, the vectors, are very dissimilar. And that is what we call discriminability. If the features are very dissimilar, when you compute the features from images of two different classes, in this case, two different persons, okay, you want them to be different. And then you say that the feature has a lot of discriminability. These features are very good. Okay, because that carries a lot of discriminability. So you compute these features, you end up with this. You compute the same set of features from a different person, so which means the features are, you can say, very distinctive. Okay, distinctive, or you can say unique, in simple term, unique, and so on. So because because of which they carry a lot of discriminability. This will help us in discriminating between, basically discrimination is nothing but classification, discriminating between different classes. Here I'm just taking two classes for for a simplified discussion, but in general, yes, it's more than two. Okay, depends on the problem. You may have 100, 1000, 2000, so on. Okay, so multiple classes, but regardless of the classes, you want them to be interclass, to be very different. Okay, so that is what we call discriminability. If they are very different, they have a lot of discriminability property, and which will help, which will make our task much easier. If the features have features that you obtain at this point, if they have a lot of discriminability and a lot of invariance, and then your task becomes much easier. Okay, your classification task becomes much easier, and that is why signal processing, image processing researchers, they focused entirely on this. Okay, developing superior techniques for pattern representation, feature selection, and so on. Because once you do that, the rest of this stage becomes much easier. You can just use some simple techniques like existing techniques like this and form. So, but of course, this is not easy. You need a lot of expertise in signal processing, image processing, and so on. Yeah, now let's briefly talk about what are the challenges that we face, uh, specifically in the context of visual recognition. Now, the visual recognition is when you have an image as an input. Okay, so you're performing recognition, pattern recognition, but with image as an input. Okay, so we call it visual recognition. So if you go back to this examples that I listed here, so this is a visual recognition. This also is a visual recognition. In order to perform reading, recognizing handwritten characters or typewritten character, you need to first compute. So when you're designing machines, you need to first capture an image, okay, and then you can recognize the characters. So whereas these are not visual recognition tasks, but the problems remain more or less the same. Although I'm not going to talk about speech recognition and speaker recognition, so I'm going to limit my discussion mostly to face recognition or any other visual recognition tasks. But remember, the problems and the challenges that we face are very similar to any other recognition. Okay. Now, yeah. So now, as I said here, I will also clarify. I've been saying that recognition is a more broader term, and then classification is a specific task. So now let's also understand in recognition, what are the other tasks that are involved. Okay. So, so let's look at specifically image recognition or visual recognition. Sometimes, in computer vision, they call it also object recognition. Okay. So visual recognition, specifically the object recognition, because we're trying to recognize objects in the image. Okay. So which is actually a very important, very basic computer vision task. Now, where you have primarily, you have two tasks. One is image classification. What is image classification? You have an image, okay, having a primary object. There may be something in the background, there may be a small ball or whatever, right? But there is a primary object in the image. And what is expected is, if this is given as an input to your algorithm or your system, what you expect is, in image classification, what you expect is just the prediction of the class it belongs to. Okay, so in this case, if you give this as an image as an input, you expect the the system to predict, or the algorithm to predict the class. In this case, the primary object is cat, that you can see here, occupying the most region in the image. Although there is, of course, wall in the background. This is the primary object. Therefore, you expect that the output is cat. Okay, so it's basically a very simple classification problem. Now, if you want to draw, if you want to have some other example, for example, in biomedical signal processing, I already mentioned to you. Let's say you have an ECG signal, and this is the input. Now you're trying to classify this as normal or abnormal. Okay, so it's a very similar problem. Of course, how you approach this problem is very different. But what I'm trying to talk about is broadly. So this can be called a signal classification problem. Okay? Just like image classification problem, so it becomes a signal classification problem. Here I'm just taking two classes, but it can be more than two classes as well. Okay, image classification problem, in fact, is a multi-class problem. But of course, it's challenging. There are challenges. We'll talk about some challenges as well, but less challenging as compared to this particular problem. What is this? This is called detection, object detection or object localization. Now, what is detection or object localization? Here, we are not detecting anything. We're just trying to classify the entire image. Based on the primary object, we are trying to classify the image or predict the class it belongs to. Whereas here, look at this. Here, in fact, you have multiple objects in the image. Okay. So you cannot perform classification of this because you have multiple objects in the image. So you cannot have just one class. You cannot predict that, it belongs to one class. Okay. There's a van, there's a bicycle, there's a dog, and so on, multiple objects. So what we do in this case is, so here we try to localize. Localize means detect where each object of interest is located. So in this case, we have done it with the help of a bounding box. We call it bounding box. So sort of a rectangular, region. We try to identify where the objects of interest are located. Here we see that mainly three objects of interest are detected: van or a car, whatever, and the bicycle and the dog. And then also, not just this, you need to also identify, recognize this, so that this is a van and this is a bicycle, this is a dog, and that is a complete object detection or localization. Okay, so that's, of course, more challenging problem as compared to classification. This also is recognition problem. Okay, so that's why I said, this is a broader term, whereas classification is a specific task, much simpler, but this is more challenging. Okay, so again, one more example, if you want to relate it to, because the theme of this workshop, or this faculty development program appears, I think, is on biomedical signal and image processing. So you can think of this example as well, where, for example, you have MRI images of the brain. Okay, so we are looking at tumor. Okay, so you can see here you have, these are multiple images, of course. So for example, here, this one image, if you focus on this image, here is where the tumor is. Now, given this as an input image, now you're trying to detect, okay, localize the tumor. Okay, and then if you have, let's say, multiple kinds of tumors, okay, benign and so on. So then comes that recognition part, classification. Okay, so as I said, once you detect an object of interest, trying to identify this as car or van, that becomes that is of course complete detection. So we first localize and then recognize. So that's what is involved in the detection. So similarly here, so given this image, trying to, here it's not bounding box, it's actually we are trying to identify the entire contour, the boundary of this tumor, because we want more precise. So okay, if you want more precise, you can of course go for, here as well, you can go for detecting. The only thing is you have to change the way you train the model. Okay, so the way the approach has to be changed, but then output will be in the form of a your contour, okay, boundary of the object. Here that precision is not required, therefore we're just trying to detect it with the help of bounding box. So here we're trying to identify the exact boundary or the contour of the object of interest, which is tumor. You can see here in this case you have, in fact in some cases you have multiple regions as well, okay, which are detected as tumors. Okay, so this, you can think of this as a this is nothing but a detection problem. Okay, now, yeah, I already mentioned to you. So you in fact, this example you can see here, this is multi-object detection. Okay, so multi-object detection, here as well you can think of, first think of as a you can think of a simple problem which is single object detection. Here it's actually a single object detection. You can see here, this is image of a scene. You have an object. Okay, so there's only one object. So you're not just performing classification, you're detecting the bounding box here. Okay, therefore this is a detection problem. You detect this object first with the help of this bounding box, and then try to identify, recognize rather, what it is. So then cat. So therefore it's not classification problem, it's a object detection problem. Single, more specifically, single object detection problem. Okay, so again, as I said, you can be detected with the help of a bounding box, or if you want more precise detection, you can go for a boundary, okay, or a contour. And more general detection task is when you have multiple objects. Okay, so again, in fact, I have the one that I've taken here. This has multiple objects. Therefore, in general, it's localizing multiple objects and then recognizing this as a cat, this as a dog, and so on. Okay, this is more that's why we call step beyond this, it's more challenging. Okay, now what are the challenges that we come across? Again, these are not very limited to these images. These are in general true, and not just in for image or visual recognition. This is in general true for one-dimensional signal processing based recognition tasks as well. Okay, so now, what are the challenges that we typically face? Specifically, intra-class variations. Okay, and that is why I said your features should be invariant to this intra-class variations. Okay, your features ideally should be invariant to this intra-class within the class variations. Let's look at that. For example, background clutter. Look at this. Both, otherwise, if you, let's say if you're performing image classification, okay, image classification, given this input, what you expect? Output should be cat. So similarly, given this image as input, output expected is cat. However, what are the challenges that we see here? Yes, both belong to this image and this image belong to the same class. Okay. However, look at the background here. Okay, so object, if you focus only on the object, yes, they will have a lot of similarity, in terms of characteristics, the shape of the ear, whatever, the face and so on. So if you only focus on this part, yes, there is a lot of similarity. However, background is very different. Not just different, in fact, the other challenge that you're seeing here is that we're going to face is the background is very similar to the object of interest. Okay, so here as well, look at the background here, the objects in the background, and that is why we call it clutter. Okay, irrelevant information that is not important, but very similar to the object of interest. So when a model or a technique which tries to predict the primary object as cat in this case, it will definitely face a lot of challenge, because in order to focus on this part, you need to first identify this part, right? Because whereas here you see the background also is very similar. Similarly here, background is very similar to the object of interest, and that is causing a lot of problem. Okay, so that's what we call background clutter. Now, Yeah, so you can think of, for example, if you're talking about speech processing, there may be a lot of noise in the background. Okay, so and noise can be of different kinds as well. Traffic noise, if it's captured in the outdoor scenario and so on. So all this will actually cause a lot of, it may be the same person speaking in a very controlled environment or in an outdoor environment with a lot of background noise. So although both belong to the same class, in if you're performing, let's say, speaker recognition, so the user is the same, the person is the same, but here he is speaking in a very controlled environment, very nice signal, uh, very less noise. But here he may be in an outdoor scenario, a lot of noise and so on, background noise and so on. So that is going to cause a lot of challenge. That's what I'm referring to. Okay, so you can relate it to the problem that you are working on, or in your area of research of interest. Now, the other problem, of course, is illumination. Okay, so look at this again. Both of, if you perform classification, yes, both belong to the same class, right? So this is also, you expect the output to be image. Here also you expect the output to be cat. Sorry, cat in both cases. Now here it is a well illuminated object, a lot of features are visible, and for any model or any technique, this should be a very trivial task. Okay, predicting this as cat is not going to be a difficult problem. However, here if you see, why is it so? Because the illumination is in the background here. Okay, and because of which the features of the object of interest is not very clearly visible. We can actually, human vision system, we can actually look at this as well, how our human vision system, how well it performs, right? So even with this contour information that we see, we will be able to recognize this object. But how well a model or a technique will perform, of course, we have to evaluate it. Okay, we cannot. But what I'm trying to say is, this definitely is a challenging case for any approach to identify this correctly as a cat is a challenging problem. And that here is because of elimination. Now, the other problem can be occlusion. Okay, what is occlusion? Part of the object of interest is not visible to the camera due to whatever reason. Okay, here, some sort of a funny examples are shown, but that's not necessary. For example, if you talk about, I mentioned that already to you, right? So if you're talking about face recognition, so the user may be wearing a mask. Okay, so in fact, during the COVID time, if you look at the literature, a lot of researchers actually focused on this. So they just took some existing face recognition algorithms, and then, or commercially available face recognition systems, and then fed some inputs to the model or the system where the users are wearing mask. So when you wear mask, so a lot of these facial features are not visible. Okay, so now if you compute the same set of features from this image, so of course some of the features will be not incorrectly computed as well, because the features around the nose, mouth, these will not be, you will not be able to compute it correctly, and therefore the performance of the system is going to deteriorate. Okay, so this has been sort of, if you look at the literature, if you look at the research works during the COVID time, you'll see a lot of people, you know, looked at this problem, how well face recognition, how they cope up with this occlusion problem. Okay, and then of course, you can imagine other things like, wearing a headgear, cap, sunglasses, and so on. A lot of these are definitely going to pose challenges. And here you can see your just an example, right? So not the entire object of interest is not visible. It has put on some blanket or something. Here it is hiding behind this, the grass, and therefore part of the object is not visible. Again, these are going to be challenges. Okay. Similarly, deformation. Now, deformation is nothing but a object that changes its shape. Okay, changes its shape. Now, if an object, not all objects are rigid bodies, right? So if you have a rigid body, yes, it cannot change shape. But a lot of times we see that, even our face is locally deformable. Okay, locally deformable. What I mean by locally deformable is, for example, expression changes. If you change our expression, right? If you have a neutral expression, now if you change, if you're laughing, your mouth is wide open. So this is actually can be an example of a deformed face. So the same person, but expression is very different. Okay, so your mouth is wide open, so that is locally deformed shape image. So because as I said, the face is locally deformable, although you cannot completely change the shape, but then locally you can change some shape, right? So those are again, if you look at the literature, people have done, expression invariant face recognition and so on. The techniques that are invariant to expression changes. Okay, so there has been a lot of research in this area as well. But these are basically the challenges that we typically face. Okay, so again, here you see here, the object remains the same, but in two different shapes. So if your features, some of the features are shape-based features, they are again going to cause problem. Okay, you can't rely on these features entirely to perform recognition. So how do we do it? Yes, so we want basically, yes, although this is all sort of idealistic thing, we want our features to be invariant to these intra-class variations. Okay. Yeah, so now let me know if you have any questions. Otherwise, we still have some half an hour left. Yeah, so we'll continue. So let's try to understand how, if you look at the traditional way. So we'll begin with, so I mentioned to you your, yeah, okay, the pipeline of pattern recognition. So let's try to understand how traditionally the traditional approaches. Okay, so how do we typically do it? So although we briefly discussed that part as well. Okay, so where we actually use some signal or image processing techniques here, most of the time transforms and other generic feature descriptors. So I'll mention about those as well. Okay, when it comes to image-based recognition, so we use a lot of these generic descriptors. Okay, so which will actually work for different applications. Now, and what has been towards the end, I'll also mention, and we'll also talk about how in recent years, with advancements in deep learning, how this has been now, how this in recent years, with advancements in deep learning, how this has sort of, there has been some sort of a paradigm shift. Okay, we'll look at that as well. So it's important that in the traditional approach, we had signal or image processing until this point, and we had machine learning in the last stage. But you will see later that with advancements in machine learning, of course, now we call it deep learning, okay, which is actually a sort of a subset of machine learning. Now we see that this has actually taken, the entire this. So now we have this deep learning architectures that perform, we don't call it pattern representation. We don't perform this explicitly. And that is why we call it representation learning. Okay, so we learn the representation now from the data. We learn these models will learn the representation. Okay, so we call it representation learning, and then perform classification. So you can think of this way. Earlier the machine learning was limited to the last stage. Now you have this entire thing is a trainable model. Okay, you can train a model which will learn the representation, compute the representation from the data. The data may be pre-processed or raw data as well if no pre-processing is required. And then once you have the pre-processed data, in most cases pre-processed data, this this model will actually learn the representation. How it learns will, if there is enough time at the end, we'll also briefly talk about that, and then perform classification. So that way, our task has become much easier in most cases, right? In most cases, this approach um, yields better results, state-of-the-art results as well. Deep learning models have in most computer vision tasks, specifically visual recognition tasks, they provide significantly better results than the the traditional approaches. Okay, so the current state of the art for most visual recognition and in general computer vision tasks as all are based on deep learning models. Okay, so that way this has made our you know life easier, because you don't have to develop an algorithm specifically, or you don't have to develop an algorithm for this. You can focus on the architectures. Okay, you can develop an architecture more suited for that particular application, so that it extracts features, maybe improve features, and there are several concepts around it now, like attention and so on, so that the model focuses on the regions of image or signal that are more important, and then give it more weight and so on. So yes, there has been a lot of improvement as well. But again, I say here we don't need to focus on the techniques that will give you better representation. Okay. So this can be learned with the deep learning models. So here, yeah, here I'm talking about how traditionally it was done. If you look at, for example, face recognition, the example that we've been considering. So in the very beginning, okay, so this was even before the completely automated face recognition system was developed. I just wanted to provide you the history, provide you sort of an overview of how this has evolved. Okay, the technology evolution. Now if you look at even before the completely automated face recognition system was developed, we call it therefore partially automated system. How is it done? So in fact, at this time we did not even have, I believe there were no cameras as well. So what we do is, if you have to perform face recognition, the person, they had this sort of a system somewhere. The person will turn up, and then you have an operator. Okay, so you have an operator who will look at this person, and then this person is actually generating the feature vector, this operator. Okay, so it's not an algorithm that performs, there's no image capturing, so on. This person looks at this person's image, and then, so see, as I said, he will describe this in this feature vector. How? So it's like, he has certain independent variables already predetermined. Okay, long years. Now operator will give a score, for example, in the range 0 to 5 or 0 to 10, whatever. Okay, a score, if he finds that the user has a long year, he might give a score maybe a 4 or 5. Okay, so that's how this representation is generated. This operator generates the representation by giving scores for long ears, wide eyes, and so on. So, and once you have this vector, and then of course, you can, for example, you can use Euclidean distance to compare the vectors and decide whether it is similar, dissimilar, is it of the same person? No. So that part was done, and that is why it's called partially automated. So this feature computation, feature extraction was performed by a man, and then matching was performed by the machine. Okay, so interesting. And there is, of course, no image involved here. But then came in the 1970s, this is actually a very significant contribution. Okay, so this professor, he's actually an emeritus professor at CMU, and in fact contributed significantly later on as well. This was his PhD work. When he was a PhD student in Japan, so he developed the first completely automated face recognition system. So again, the idea was simple. So you had at that point, I think there was a grayscale image that was captured by the camera, and once a grayscale image was captured, no color information basically. So he performed edge detection. Okay, so if you're familiar with basic image processing techniques, edge detection is one of the simplest techniques that you can perform. Just try to detect, where there is significant change in the intensity values. So you get this, sort of a sketch. Now, from this image, so sort of a schematic of it is shown here. This is not how edge image looks like, but it's sort of a schematic of that. So once you have the edge image, you can actually, he wrote an image processing algorithm. Okay, so he developed an image processing algorithm that computes, like, you can see here, these are the features. He proposed a complete 16-dimensional feature vector. What are those features? We will not look at all this in detail, but basically you can see some of these, width of this left eye, right eye, distance from the center of this eye to this eye, some angular measurement to capture this shape of the nose, and some distance measure as well. Again, some distance measure, width of the eye, to capture the jaw shape, curvature, some angular measurements, and so on. So putting together all this, So in fact, he performed, interestingly, if you read the paper, he also performed feature selection, but not using some technique, because I don't think any systematic technique existed at that point. So instead, what he did, he experimented with several feature sets. So initially, he had a lot of features. Okay, so you can think of this as the original set, and then he tried with different subsets, and finally he proposed that this 16 features are very important. And with these 16 features on a very small data set at that point of about 20 users, 20 people, so he achieved a 75% accuracy. Remember, this was the first work, and then later on, if you know this professor, yes, he contributed significantly to computer vision, several other techniques as well. So, and this is how, just to give you an idea how the approach was, how they approach these problems. Okay, so basically based on some domain knowledge. In order to perform this, you need to have some domain knowledge, right? So that, these features are useful, eye features, nose features, mouth feature, this shape, curvature, and so this requires what we call domain knowledge. Okay, so this is how initially this was done. Okay, I'm talking about this stage, pattern representation stage. Okay, so the initial methods all relied on some domain knowledge. Okay, so based on some understanding, yes, these features might work, or they may have consulted some experts as well, and then try to identify the features that are important. Okay, that will capture the underlying pattern, and then can be used for classification. Now, yes, one more example if you're interested. This is actually from this this book. It's actually a classic book on pattern recognition or pattern classification by Duda, Hart, and Stock. They have this example, although this problem is a very interesting problem. It's a industrial vision system. We have, it's a complete example, real world example. So where you have, when you catch, this is about recognizing the two species, two kinds of fishes, the sea bass and salmon. Okay, so based on the image. So why is it important? So when you catch fish from the sea, so it's all sort of mixed, right? So you bring it in a bag, for example, so it's mixed. But remember, in a fish packaging plant, where you package them before you send it to the market, you need to separate them, because this may be selling for, let's say, 100 rupees per kg, maybe this is 200 rupees per kg, right? So then in that case, you need to separate them, package them separately. So it's a packaging plant basically. Okay, so here the idea is, can we automate the system? Of course, you can rely on manually doing this. If there's an expert who can recognize this and recognize this, so you can perform this manually, right? But instead of it, can we automate this process, which will become more efficient as well? You can run the system, 24/7 and so on. So it's, not sort of vulnerable to fatigue and other factors if it's done by a manual expert, human expert. Now here, what you do is, you can have, for example, a robotic arm to pick up one fish at a time, drop onto a conveyor belt. So as this fish moves on the conveyor belt, you can have a camera. I can see here, I'm not sure if this is visible. It's mounted on top. So it's mounted on top, captures the image of a fish. Okay, and then here is where we need to focus on. The rest of the things are not in our domain. Basically, once it captures the image of a top view of an image on the conveyor belt, you can see here they have also made a nice setup here. The background is made uniform white, so that your feature extraction, maybe if you're interested in what we call segmentation, okay, identifying detection basically, okay, the region of interest, that becomes much easier on a uniform background like this. So you can compute some features. What are the features? We'll talk about that as well. So basically classification, and then once you do that, you have a robotic arm. So once, based on the output of your decision stage, a robotic arm will pick up the fish. Okay, if it's found to be salmon, maybe it will pick up and drop here. Okay, if it's predicted to be sea bass, it will pick up this. Okay, a robotic arm will pick up and drop it here. So it's an entire system. Of course, you can think of that way, but here we are focusing on this part of it, the pattern recognition part of the system. So I hope that clear to you. Now if you are asked to, right, as an expert on pattern recognition, image-based recognition, pattern recognition, if you're asked to design or develop such system, how do you approach? The first thing is we may not have any domain knowledge. We may not even know what are the important features, what are the features that we can use at this stage to perform classification. So you may have to consult an expert. Okay. So let's say you talk to that same expert who actually a human expert who can do this, by looking at this two fishes, you can recognize them. Okay. So you can consult such experts. That's where, domain knowledge comes into picture. You can approach this expert, and let's say expert says that generally he says that sea bass is longer than salmon. Okay. He provides you this information. He says in general sea bass is longer than salmon. So he says maybe you can use length feature. Okay. So maybe, because remember, when a human expert performs this, he may not rely on exactly the length. He will look at completely, in entirely. Okay. So sort of holistically, right? So he has some multiple attributes, he will characteristics that he will depend on. So one of them, he said, one of the most important attributes of characteristics, he said, is the length. He said, yes, sea bass is generally longer than salmon. Now you want to sort of verify this, whether it's true. So what you've done is you have collected some images of both these classes, sea bass and salmon. So let's say you have collected 50 images of salmon, okay, and then 50 images of sea bass. Now we also ask the same human expert to provide you the labels. Okay, label, which means he looked at this image and he said, yes, this is salmon, this is salmon. So he is, this is what we call annotation or labeling, which is also required if you're trying to develop this system here, because classifier will require labels, right? Because it's supervised, it's trained in a supervised setting. Now you have collected these images as well. So the expert looked at each image. He said, yes, these are sea bass, and so on. Now you have the images, you have the labels. So somehow, given this image of a fish, you can also write a program, image processing algorithm you can develop to compute the length of this. Okay, so length in, in pixels and so on, whatever. So from each image, you computed this length feature. Okay, so it's a scalar value, and you have the corresponding label as well. Now, if you plot what we call histogram, basically this is more specifically we call it class conditional histogram. Why is it so? We are plotting histogram of the length feature. So on the x-axis, it's already mentioned here, the length, and y-axis, it's histogram. So I believe histogram is familiar to you. Typically the number, which means that what it means, typically you do the binning as well. You don't consider every possible value because this is a continuous variable. Okay, it's a continuous variable. So what we typically do is we consider a small range. Okay, for example, here we consider, let's say 5 to 7 and so on, right? 5 to 7. So count the total number of data points, examples, where the length is between 5 and 7. So it appears that in this range you have around, let's say around 10 or 11. Okay, so that is what we call class conditional histogram, because we have plotted it separately for salmon and for sea bass. Okay, so from the data that we have from each image, we computed the length feature. We have the class information. That is why we're able to plot class conditional histograms, distribution basically, right? Now tell me whether whatever information he gave you, that sea bass is generally longer than salmon. Is this correct? Is is sea bass generally longer than salmon? Is that correct? Are you able to verify this? The second question is length a good feature? When it comes to classification, is length a good feature? Okay, there are two things here. Yes, this is correct in general. The reason is you look at the histogram peak. This peaks around here. Okay, yes, one feature alone may not work, but what I'm trying to see is, for simplified discussion, let's consider one feature at a time. Yes, in practice, we will not rely only on one feature. Okay, but what I'm trying to see is what he said was correct. Sea bass is generally longer because if you look at the peak of this histogram, it happens here around 20. The length is 20, and that is where you have significant number of them, maybe 20, 22 plus, maybe 25 of them. Okay, 25 of those images, data points or examples have a length around 20. And similarly, look at the other class, the histogram peaks around this, okay, around 10, slightly less than 10. So if you look at that peaks, yes, it's true that sea bass is in general longer than salmon. But second question, is it a good feature? The answer is no. The reason is, look at the overlap of the two histograms, two distributions. The significant overlap, this starts here, okay, and you see here it extends to this point, okay. So it starts here, although it peaks here, it extends to this point. The other one, it starts here, peaks are well separated, but there is significant overlap, okay, which is why this feature is not a good feature. When you develop a machine learning algorithm, if you rely only on the length feature, it's not going to, because I think you're familiar with this. I think you're familiar with errors in classification, right? For example, if you talk about, if you consider this to be the positive class, this to be the negative class, you can see here, all this would be, if you count the total number here, or in general area under the curve, this would be false positive. These are actually belonging to the negative class samples with a threshold like this. If you set a threshold at this point, somewhere here, where the crossover happens, if you set a threshold here for classification, okay, so all this would be false positive. Similarly, these data points, these examples will, with this threshold, will be classified as negative because originally they are positive, belonging to positive class, and this is called false negative. You will have, with this feature and with this threshold, you will have significant false positives and false negatives, which is undesirable. Correct? Is it okay with you? Yeah. So now what you actually desire, what sort of distribution do you expect? Now let's say you went back to the same expert. You asked him. You said you're not happy with the length feature. So is there anything else that you can suggest? So he says lightness. Now what is lightness? Again, we are not interested in that. So he says lightness is a good feature. You can explore. Now again, what you did from each image, you somehow computed. Again, some image processing algorithm, you compute lightness feature. So you did the same exercise. You plotted. Now class conditional histogram of the lightness features. Now tell me, is this a better feature than length from the histograms? Is it a better feature than length feature? You can compare this feature, right? You can see here significant overlap. Yes, overlap has significantly reduced. Okay, so which means if you compute now, if you use this feature for classification, you will end up with significantly less false positives and false negatives. Error, basically false negatives and false positives are misclassification, errors in the classification. So you will be able to reduce significantly those with this feature. Yes, in practice, I understand you will not depend only on one feature, but what I'm trying to say is ideally what you expect is distributions like this. Two well separated distributions. If you had these sort of distributions, your task is very simple, right? So you just have to identify some threshold somewhere in between these two, and then any image in that, if you compute the feature, if it's less than this threshold, you will classify it as belonging to this. When you have a given image, test image, when your feature is greater than this, you would classify it as belonging to this class. So this is what you ideally expect. Two well separated distributions, okay, histograms. Whereas what you actually get is, okay, what you actually get is here in this, you obtained is uh, slightly, of course, it's not as bad as this case, but still there is some overlap of these distributions. Now let's look at a case also finally. So I think we have 10 more minutes. Yes. So let's consider, what if you have two features? Okay, again, features are, what are these features? We are not concerned. Let's consider two features. Or you can simply say feature one and feature two. In that case, what happens is, now we cannot plot the histograms because we are now in the two-dimensional space, which means from each image, we compute the value of feature one, the value of feature two. Okay, so from each image you write an completely automated manner. So it's an image processing algorithm you can develop, which computes the value of feature one. So this is how, and the corresponding label. Okay, so for each image you have this 2D input feature vector and the corresponding label, and that can be shown as a scatter plot, right? We call it scatter plot, specifically 2D scatter plot. Okay, again, for simplified discussion, we are considering only 2D. We can even go up to 3 dimension, but beyond that we cannot, because scatter plot cannot be plotted for anything beyond 3D. So now with 2D, let's say you have this sort of a distribution. Now imagine if you're trying to classify using, this is called actually decision boundary of a classifier. Okay, every classifier has a decision boundary. Okay, which means if you're using a linear classifier, sorry, a classifier having a linear decision boundary. Okay, so which means in this case, because it's the 2D space, linear function is a line. Okay, line. So classification is all about finding the parameter of this line. So line can be written as y equal to mx plus c. So finding these parameters m and c optimal, because see, line can be anywhere, right? Line can be here, line can be here, line can be here, line can be here. Optimal line, line that separates these two classes. So let's say you somehow trained a classifier that has found this line. So this line, you already found the slope and its y-intercept. So this is what we call decision boundary of the classifier. Now with this decision boundary, you can see that if you perform classification, how do you perform classification? So given an image of a fish, you compute the two features, and if that point falls on this side of the line, you would classify it as belonging to this. If this point belongs to, sorry, if it falls on this side of the line, you would classify it as belonging to sea bass. So on the training set, you would see that these would be misclassified, not significant number of them, but these would be misclassified because these are belonging to someone, but on this side of the line of your decision boundary, and these are belonging to someone falling on this side of the decision boundary. So this will be misclassified. Now, the point is, ideally, you want something like this. Okay. Ideally, here also, what do you expect? You expect two clusters like this, well separated clusters. All these points forming a very compact cluster here. All these points forming a very compact. Compact means they occupy a very small region in the 2D space. Why I want compactness? I'll talk about that as well. Okay. In fact, the two properties, you know, I don't know if I've, yeah, sorry. These two properties I talked about here. Okay, these two, discriminability and interclass. This will now be reflected in your scatter plot. Okay, how? This will be reflected in your scatter plot in the feature space. Now, what we're trying to visualize is a feature space. How they get reflected? Discriminability will cause, if the features have a lot of discriminability, which means, okay, they will be far apart. This point and this point belonging to the two different classes will be very dissimilar, far apart. Similarly, if you have a lot of invariance, the points within the same class, okay, intra-class points will be limited to a very small region. Compactness, that is what I said, compact. Compact because of this property, separation because of this property. So if this property is very high, if a set of features that you compute has a lot of discriminability, your points will be far apart, and similarly, if the features have a lot of invariance to those factors affecting the intra-class variations, then you will have more compact clusters. If not, the clusters will be spread. Okay, so both are very important, and that is how they translate into this. Okay, so well separated as well as compact clusters is what you actually look for, what you desire. So again, in that case, our classification becomes much easier, right? You just have to learn a classifier. In a linear classifier or a classifier having linear decision boundary will perform very well. So for example, yes, for this case, for example, if you look at it, so you have a face recognition problem, okay? Specifically a 3-class problem. You're trying to classify. Now, I'm showing here, you see a lot of points here. What are these points? Actually, each is an image of a person. From the image, you computed some features, set of features, typically high dimensional features. Then for visualization, what we do, we cannot visualize this directly. So we use some sort of a dimensional reduction. You can use, for example, PCA, the simplest technique. So from this high dimensional set of features, you can reduce it to, here we have reduced it to 3D. You can see here, this is a 3D space. You reduce it to a three-dimensional space. So K is 3 now. So N is whatever, okay, original feature set. From that, you reduce it to 3D. So this becomes a point now, okay? So from each image, you compute the original feature set, reduce the dimension. So these are all different images of the same person. So this is just a representative image for this class. Okay, similarly, each point is an image of this person. So multiple images of the same person. So you forms a very compact cluster. This also forms a very compact cluster, and this forms a very compact cluster. A very good situation here you have, right? And these clusters are also well separated because these are different, belonging to different classes. Okay, so again, this is what we desire, but in practice, yes, there would be some sort of overlap, and that will definitely lead to misclassification. Okay, so I think I'll just summarize and then, yeah, so in general, our goal is two stages are very important. The last two stages, okay? So in the PR pipeline, pattern representation is very important. Having the right features, because it will, if you have the nice set of features, for example, this, your classification becomes much easier, okay? So this task becomes, at the same time, uh, as I said, in practice, you may not be able to always get these nice set of features which are well separated, compact, and so on. Therefore, this also is important. Having a good classifier that will, so for example, here you can think of this way, right? If you want to improve with the same features, if you want to improve the classification, what can you do? You can go for a more complex classifier. For example, a classifier like this. This this is a nonlinear, clearly a classifier having nonlinear decision boundary. Okay, now this is likely to perform better than a linear classifier. Okay, so that is the other approach. One approach is, of course, you can explore different features so that you get a distribution like this if possible. Other way, you can actually go for a more complex classifier which has a nonlinear decision boundary, and then it will reduce the errors. So both stages are very important: appropriate features and classifying them effectively. But the problem with this conventional approach is, as I told you, for in order to extract lightness feature, length feature, you require domain knowledge. Okay, that may not be present in all cases, and that led to researchers exploring what we call generic feature descriptors. So they said, of course, these are only applicable for visual recognition, but remember, even for one-dimensional signal processing, some of these variants have been tested. Okay, for example, LBP, there is one-dimensional LBP. Okay, which is something like, you have a signal, regardless of the problem, you can use 1D LBP technique to extract certain features. Okay, basically it captures the local fluctuations, how the signal sample varies locally. Okay, and then based on this, you can perform classification. Okay, so in fact, even you can think of this way, all the transform based techniques are generic feature descriptor techniques. Okay, so if, for example, if you're using a discrete wavelet transform, regardless of the problem, you can use it for example, speaker recognition, you can use it for speech recognition, so on, multiple different problems. Okay, so and these are some of the generic feature descriptors in computer vision, very effective, and at one point they did provide state of the art performance. Okay, these are more generic in nature, so you need not worry about, for a given problem like this, need not worry about what can be good features. You can just apply one of these techniques, it will work. Okay, because these are mostly based on texture information. Some specific techniques, although at this point I will not be able to discuss this in detail, how exactly this works, and you end up finally with a feature vector which you can compare and so on. And then similarly, you have a separate method which is actually a key point based method. It tries to identify, given an input, it tries to identify a set of key points and then performs matching based on the corresponding points matched. It establishes the similarity. Yes, at this point I'll stop, and then yeah, finally, we are moving into. So researchers at one stage, they also felt these are, although this was developed as a generic features, having certain advantage can be used for different problems, different applications. But at some point it was felt that these are too general in nature, and a specific set of features for a problem might work better than generic features. Okay. And that led to what we call representation learning. Okay. Can we learn, given some data, can we develop, in fact, that is what now these two stages, the last two stages have been actually merged into one, where we actually use some deep learning models that will learn the representation and then perform classification. So the idea of representation learning, actually came from here, right? When it was felt that these generic descriptors, although they perform well, maybe we can achieve better performance if we compute some features specific to the problem. Okay, that led us to representation learning, and the breakthrough happened in. Although this idea is not new, but the breakthrough happened in 2012 with the first, not the first, in fact, the first CNN was proposed in around 1989. It did not gain much, attention. But in 2012, AlexNet actually won that competition, and they made some minor, contributions as well in this paper. But otherwise, architecture remains more or less same as the LeNet that was proposed in 1989. This won the competition, and then of course, since then there has been a lot of advancements in deep learning, CNNs, and transformers and vision transformers and so on. Okay. So all of them actually perform representation learning. Okay, so I'll stop at this point, and if you have any questions, I'll be happy to address. Yeah, let me know if you have any questions. Otherwise, uh, yeah, that's true, Krishna. Yes, your point is correct. Absolutely correct that you require, just having some model, existing architecture, just taking some existing, well-known architecture, for example, ResNet, AlexNet, and so on, applying it to the problem, definitely not going to give you a, it's of course not a good quality work as well. So focus should be on, in my opinion, at this point, focus should be on how we can improve deep learning models for a specific problem. So if you can, but if you entirely focus on feature engineering, which actually what we refer to as, I have here, I think I have here, I mentioned here as well, right? Handcrafted features. Okay. The difficulty here is, although at one point they were the state of the art, but for most of the problems now, deep learning models give you better performance. So remember, performance also, in fact, performance is the most important factor, right? For any publication, it should be better than the existing techniques. So you should, in my opinion, you should focus on deep learning models and try to improve. Yes, there you can actually bring in, if you have some expertise, right, in feature engineering. So if you can also incorporate that into the model, okay. So that is why, if you look at the deep learning models also, it's not just simple models. Some people have, uh, looked at some multitasking, for example, infusing some domain knowledge and so on. So there has been a lot of research in this area as well. So at this time, my opinion would be to focus on deep learning models, but not just use something that is existing. Okay. So come up with some novelty there. Yeah. So Ruchi's question, can we use representation learning for signals? And yes, there are, uh, you know, simple DNNs, or people have even applied CNNs. How? So from the signals, you can obtain some sort of a 2D representation. Okay. So again, this is the very classic, approach. So given a speech signal, for example, you can obtain, the spectrogram. Okay, the spectrogram is going to be a 2D representation, and then that can be fed into your CNNs, because remember, CNNs were originally developed for visual recognition, okay, image based recognition task. So if you're dealing with signals, you somehow you have to convert or transform it is into some sort of a 2D representation and then feed that into the model. Yeah, so good book for feature engineering, not specifically feature engineering, but it's part of your machine learning, right? So any good book on machine learning would actually will have feature engineering part as well, right? So you have in fact, the feature selection, this is also part of feature engineering, dimensional detection. So all books on machine learning, pattern recognition will have actually feature engineering. We'll discuss feature engineering as well. Yeah. Any other questions? Okay. Thank you. Thank you all. And so shall I end the session then? Shall I leave the?
Okay, sir. Thank you, sir. Hemant sir is not here at the moment. So
Okay. Fine then. So thank you then. Bye.